NanoHub U, online instruction.
Hey everyone, now we're going to continue our discussion about wave optic matrices. We briefly already went over T matrices and R matrices, and now we'll cover S matrices. So here the concept of the S matrix is to look at the connection between incoming waves and outgoing waves from the boundaries of a certain region, which may be a multi-layer stack. And so mathematically, we write it in this form. And so you can see it looks kind of like a hybrid representation. So we have like the up components at the top of the stack, u p plus 1, and the down component from the bottom of the stack, d0, depends on the S matrix, which is actually written in this hybrid form, TRRT, times the incoming elements u naught, so incoming from the bottom, and then dp plus 1 incoming from the top. Okay, and so you can obviously see just physically that the transmission from the bottom to the top must depend on this first element, t uu of p, and then the reflection at the bottom, for example, would be r du of p. And so S matrices have a couple of key properties. If you don't have any loss in the system, then they're unitary, which basically means that the adjoint of S times S itself would be equal to the identity matrix. And so why is that valuable? That tells us that there are no exponentially growing terms. In other words, mathematically, all the exponentials that are present in the system, if there are any, would be in the denominator, not the numerator. And so that's a very valuable property and is physically reasonable. So the reason why it makes sense physically is that you know that the amount of energy coming into the system in the absence of gain or something should not exceed what's being lost. And so even if you do add loss, then you expect that things will just decay further, so you'll have less light coming out than you had going in. And so that physical motivation has allowed us to create a mathematical representation that gives us greater numerical stability than the T matrices. And so how do we actually construct them in detail? So what we do is we write down just an ABCD matrix from the T matrix formulation. Okay, so that's simple enough. And we can actually then rearrange everything so that we have something that matches up with the formulation of the S matrix. Okay, so we basically are just moving around the terms, basically writing out like term by term, like all the equations, and then re-equating them. And so then that gives us something like this. So we have the capital dp times lowercase d naught equals dp plus 1 minus cp u naught. And then you can see, I won't read out the second equation, but you can see you got something analogous for up plus 1, a little more complicated. And so then that actually directly allows you, just by resolving the same set of equations that we started off with in the T matrix, to write down an S matrix equivalent term. And so we're doing that analytically, so that means that there's no numerical loss in accuracy at this point. And we can then equate each of these terms that we got in this new S matrix formalism to the physically motivated transmission and reflection coefficients in the S matrix. And then, of course, as we did before, we can actually define like an S layer matrix, S tilde, which is very analogous to our T tilde matrix we had earlier, which would be essentially the quotient of two interface matrices, which we can write it as SP without the tilde, times two phase terms. And before we had phi as just a single phase term, but because of the different propagation directions, we actually have to break up the phase slightly, but it's very similar to what we had earlier. So you can see basically we have the positive exponential on the right and then the negative exponential on the left, but otherwise very similar. And then we can actually relate it to the T matrix from before. And so we basically have just rewritten that equation that I had earlier. Okay. So that was essentially this equation, but just rewritten in terms of T matrix elements. Okay. And then combining these two things, like the SP, which we just calculated, plus the phase factor, allows us to create like iteratively, like if we have like P layers of the S matrix and we want to add the P, or sorry, more accurately, we have P minus 1 layer, so we want to add the Pth layer, then we basically get to construct it iteratively, and then we end up with a matrix like this. And just keep in mind that the first two elements are on the left-hand side, last two elements are on the right. It's just hard to write them all like in a 2x2 matrix. So in the next lecture, we'll go into more details about how to construct and work with these S matrices.